So in today's video, we'll be talking about application of differentiation. Alright, what is differentiation? Basically, differentiation is a process of finding a function that outputs the rate of change of one variable with respect to another variable. For example, we want to check the position of a car on a two-lane road with no passing lanes. Assuming the car never pulls off the road, we can abstractly study the car's position by assigning it a variable x. Since the car's position changes as the time changes, we say that x is dependent on the time, or we can write it like this. This tells where the car is at each specific time. Differentiation gives us a function of derivative x with respect to time, which represents the car's speed. It is the rate of change of its position with respect to time. Why do we use differentiation? Differentiation allows us to find rates of change. For example, it allows us to find the rate of change of velocity with respect to time, which is acceleration. It also allows us to find the rate of change of x with respect to y, which on the graph of y against x is the gradient of the curve. Alright, next we have application of differentiation. First, we have tangents and normals, which are important in physics. For example, forces on a car turning a corner. So this is the graph that shows the tangent and the normal to a curve at a point. Alright, second, application of differentiation also applied in maximum and minimum problems. It is to calculate the highest and lowest point of the curve in a graph or to know its turning point, as you can see in this graph. The last one is related rates. Actually, this is the topic that we will be discussing in this video. Basically, related rates are whenever two variables both vary with respect to time and have a relation between them, we can express the rate of change of one in terms of the other. We can differentiate both sides with respect to time, and then we will be finding the derivative of f with respect to time for the function.
This is Lucas. Lucas is out camping in the woods. He is burning a cylindrical log of wood to keep himself warm. Lucas wants to know when is the right time to add more wood to the fire before it extinguishes. If the fire burns the wood at a rate of 4 cm³ per second, what is the rate of change of surface area of the burning wood when the radius is 6 cm? Let's say we have a cylindrical wood with radius r and height r plus 2 centimeters. In order for us to find the rate of change, we must find the area of the cylindrical burning wood first. To find the surface area, we have 2 pi r squared plus 2 pi r times height, which will be substituted with r plus 2. Lastly, we have 4 pi r squared plus 4 pi r, and that is our surface area. Next, let us find the volume of the cylindrical burning wood. We will have pi r squared times height, and height will be substituted with r plus 2. And we will have pi r cubic plus 2 pi r squared, and that is our volume. When we know both of the surface area and the volume, we can complete the final step, which is finding the rate of change of the surface area when the radius is 6 centimeters. Let's say the radius is 6 centimeters and the cylindrical wood burns at a rate of 4 centimeter cubic per second. Here is a strategy to solve the problem. First, we will assign letters to all quantities and identify the rates of change. Then we will find the equation of the surface area of the cylindrical burning wood. We will then differentiate the equations in step 3 with respect to time. We will have dA over dt, which equals to 4 pi 2r dr dt plus 4 pi dr dt, which will be 8 pi r dr dt plus 4 pi dr dt. dv dt, which will be 3 pi r squared dr dt plus 4 pi r dr dt. We will now complete the equation in order for us to find dr dt. dr dt will be dv over dt divided by 3 pi r squared plus 4 pi r. For the final step, we can try to solve the equations by substituting. Then solve to find the rate of change. We will solve the area by substituting r with 6 centimeters. Then we will substitute negative 4 centimeters cubic per second into dv dt. By applying the rates of change, we can see that the cylindrical wood burns at negative 52 over 33 centimeters squared per second when the radius is 6 centimeters. To solve the problems faced by Lucas, we can conclude that the cylindrical wood burns at the rate of negative 52 over 33 centimeters squared per second.
In conclusion, differentiation is the process of finding a general expression for the rate of change of a function. It can be applied in any situation that involves change or motion. Differentiation carries endless of benefits and has greatly contributed to our daily lives in more ways than one. Hence, if we encounter a certain problem where change or motion is applied, we can surely depend on differentiation to act as a method in providing us the answers.